All right, thank you guys. So you've been staring at this problem for a little bit now, where we have a rubber stopper, just like the experiment we did the other day, being spun around. The string is 1.5 meters in radius, or 1.5 meters long. The assumption is that that's the radius. It takes half a second to complete a single revolution, calculate the centripetal force, and hence the tension in the string. That part there is super critical that we understand that, right? If we're calculating a centripetal force, remember that centripetal force, if we look at a quick diagram, that is the force responsible for changing the direction of our rubber stopper. Rather than the rubber stopper traveling this way consistently, it's accelerating inwards. Its velocity at this point is in that direction, but it's accelerating due to this centripetal force, which is the net force responsible all the forces. There's no other forces acting. We're ignoring friction, ignoring gravity, etc. That creates an acceleration, so our vector keeps on running around and around. While we're here, our acceleration is now there, and our velocity then is once again a tangent to the circle going that way. How did our velocity change direction like that? Due to the acceleration caused by that centripetal force. And that's a nice, smooth, consistent thing around a uniform circular motion. Again, very rare that these things actually happen. We saw in that experiment, things probably were not so uniformly circular, were they? No, quite a lot of wriggling of the wrist up there. Okay, so probably not uniform circular motion. But we can still use the theory to model situations. Now, in this case, I want to spend a little bit of time talking about something we haven't looked at in a while, and that's significant figures. So just very quickly, I want to do, is this going to work? Hang on. I want to do A, B, and C. How many significant figures do I have? How many for A, how many for B, how many for C? Just write that under your book for me. Just a little refresher on some of the basics that we haven't looked at in a little while. Answers in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. A will be 3 sig figs. B will be 1 sig fig. C will be 1 sig fig. Okay, so really important, we recognize this 0 after the decimal does not need to be there. So someone put it there for a reason, okay? That reason is that they know it's accurate to 20.0 grams. It might have been 20.01 or 20.05 or 19.99, but their scale read 20.0 grams and they know that to be accurate. Half a second, there's only one significant figure, this one here, right, the 5. That's 0, that's meaningless. The 0 before a number. If I write 5 seconds like that, that doesn't mean I know that there's 0, 5 seconds. It's just 5 seconds. That's all I know, one significant figure, right? And then, of course, the last one, clearly only one significant figure, despite this. What would we call this again? What do we describe? How do we describe this thing on the end that we've added on? An uncertainty. So the manufacturer publishes this string and tells you it can handle a tensile strength of 5 newtons, but we do have an uncertainty of 0.1 newton. What does that mean in this context, Alex? Okay, so if it's greater than 5.1 newtons, definitely going to break. If it's between 4.9 and 5.1, it's probably going to break, but we don't know. You might have gotten lucky and your string could be a little bit stronger than the others we tested, and it might handle up to 5.09, but it won't handle more than 5.1. That's what that's telling us. Cool. All right, let's get into the actual problem now. I just wanted to make sure we have some conceptual understandings in there. So in this situation, we have a mass, which is 20.0 grams. We're going to immediately go to 0.02 kilograms. Our radius, we're going to assume that's our radius. The string's length is the entire radius. Nicola, off and away. Is 1.5 meters. And our time, let's say t, equals 0.5 seconds. Now, thankfully, you guys seem to be fairly familiar with this at this point. This is the time it takes for a single revolution. So t equals 0.5 seconds for 1 rev. And we know that that is capital T, period. No calculations required there. The time is 0.5 seconds. That was the time for 1 revolution. That is what our period is, okay? You can actually use a formula to calculate period if you ever need to. You can do a bit of a T versus number of revolutions, right? You can do that, and that will consistently give it to you. And that's what we did in that prac with 20 revolutions over however long divided by 20 will tell you how much per 1 revolution. So in this case, we're given it as a period, so we just use that directly. Cool. Any other information we need? We're told we're calculating the centripetal force, so we're looking for Fc, or as we know it to be Fnet. We're ignoring air resistance, gravity, friction, etc. And hence the tension in the string, so we can also establish that that's going to be capital T for tension. Now, see a situation here? See a little problem? Right? My net force is tension. It's clearly 0.5 seconds. Did you know that? Look, I said it here, right? T is 0. Right? Careful with your notation. Yeah? What should I use instead? Ft, not just a big old T. We already used that. Ft. Not 0.5 seconds. What does this equal? Cool, yeah, so go straight to that net force formula in your data books, mv squared over r. Cool. Do we know everything there? No, what don't we know? We do not know velocity, so we're going to have to find out velocity. Velocity equals what? Do we have a formula for velocity? Cool, yeah. This is a nice, easy formula to remember. It's circumference of a circle over the time it takes for a revolution or the period. Every 1 time around the circle, it travels this far. Velocity equals 2 pi r on t. That will be 2 times pi times radius, which was 1.5, divided by our tension, our period, which is 0.5, and we get, that's a half, so that's doubled 4. So what do we get? 6 pi, 18.85. Watts. Meters per second, yeah, it's a speed. Just because it's a circle doesn't mean we're not traveling meters. Yeah, we're just doing it in a roundabout way. Get it? Roundabout way. Anyway. No? All right. Tough crowd. What now? Why did I do that? Why did I need V? Equals, what's my mass? 0.02 times by 6 pi squared. Welcome to work with pi, yeah? Use it as a number if you want, use it as a symbol, I don't mind. Over radius, 1.5. And what do we get as an answer? Newtons. 4.74 newtons. Cool, sorry about squeezing this in, as per usual. I like to live dangerously. Sue me. What's that? Happy? No, I wasn't asking you a question. I was just picking up on the bullying here. Yeah. Okay. Will the string break? Yes or no? No, absolutely not. No. Is it possible the string will break? No, it is not. Question. Really interesting point, guys. Did you hear that? Right. If you were to take in significant figures, would. Because what's our minimum significant figure we're working with? 1 significant figure. What is 4.74 as 1 significant figure? 5 newtons. It very well could break. Now, that doesn't guarantee us it could break. What do you mean? 0.5, the 1 significant figure. Here. 1 significant figure. So this could actually be 0.54. If you divided this by 0.54, you get a much smaller number here. Your much smaller number here would give you a much smaller result here. Or it could be 0.46. do it with 0.46. Let's see what we get. So 2 pi times 1.5 divided by 0.46. 0.4, just do it with 0.46. You can do it with 0.45, but. 0.46. So we get a velocity of 20.5. We then use that velocity squared times by 0.02. The mass divided by 1.5. 5.6, which again, if you rounded, you'd get 6. Yeah? So it is actually possible, based off the accuracy of how we've measured, that we will break this string. Really good point, yeah? Very cool. Okay, I want to talk about this in terms of one other context. Does anyone want me to leave this for a minute? Anyone need it? No? Cool. Grab it off someone else if you do. Let's talk about racing cars. This is the radius of a curve. You don't need to copy this down, I just want to talk about it. Beautiful car. You're a car. All right. Active listening in 3. That's supposed to be a car. You're a car. 2. Yeah, it's a car. 1. That one as well. Let me explain. All right. Get it out. What am I, an artist? No. You're lucky I even bothered trying, not just giving you rectangles, okay? At least I put windows on it. Wait, is this a bird's eye view? It's a bird's eye view. So why would we see the windows? Because you're above the car and they're slanted. They're slanted. No, but you're slightly over to the... I don't know. Whatever. Yeah, it's a sunroof, sure. All right. Shut up. Getting bullied in my own classroom. Okay, this is quite an interesting situation to discuss uniform circular motion. So let's have a look at this. Do I need to split you two up? Last chance. It doesn't seem intuitively like it would be, but it absolutely is. When your car is driving straight, you have your momentum, you have your inertia going straight. If you want to turn, if you want to go to the right, you need a force to accelerate you in that direction. What is that force? Why friction? How do you create that force of friction? Where does that force of friction come from that you're talking about? Right, but when you're going straight, your tires and the road are still there. What's different? Why does that matter? Seriously, have a think about this. How does a car actually turn? How does it create a force sideways? When our car is traveling in this direction, I'm telling you that there is a centripetal acceleration, which is caused by some sort of centripetal force. What pushes a car sideways? What force pushes us sideways? You are right, it is friction, but how? Nicola, come sit up front. Wheels have grip, right, but we can still go straight with wheels. Why do they all of a sudden get us sideways? Huh? What pushes this way? Centrifugal force isn't real. It's us inside the car being slammed into the left door and doing, what do you call that? Corners with your siblings, because the car is accelerating that way and you're trying to stay still. So you get pressed against that accelerating surface. Inertia is what's keeping us straight. What is the force that creates us to turn? Yeah, it's friction, but how does that work? Is friction propelling us forwards? What's moving us forwards? The wheels. What are the wheels doing that moves us forward? Turning. They're turning, right? So the wheels are rotating, and that way they create actually a force on the pavement backwards. So if we imagine a wheel, this is really kind of weird stuff, right? If the wheel's rotating that way, yeah? What it's doing is it's pushing a force, an applied force, on the pavement that way. And the pavement does what in return? With what? Equal and opposite force. Where's that force coming from? Friction, right? So the wheel has an applied force due to that rotation coming from the axle, blah, 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 all the way in. And the ground pushes back with the force of friction, propelling the whole vehicle forwards, right? What changes when we go sideways? I'm not talking about drifting here, by the way. A nice controlled turn, to be clear. Nice controlled turn.
If the angle of the wheel turns, going back that way.
Right, so when we turn our wheel, we're not relying on a forward friction anymore. When we have our wheel like this, we get an applied force backwards. We're now above the wheel, okay? So the wheel's rotating upwards. The wheel's rotation is like this. Okay? The wheel's rotation is like that, and then down on the pavement underneath, and that is applied force backwards. The friction cancels that out by going forwards, okay? And we propel ourselves forwards. When we turn our wheel, yeah, that friction also gets created if we're going this way. So let's now draw a wheel on an angle. We've turned our wheel. Our velocity was this way. The friction force now acts to resist this velocity. And the friction is not the same friction that was from the wheel rotating. The friction is from the wheel trying to roll over sideways. And it can't, so the friction actually now pushes us that way. It accelerates us centripetally. Bizarre, right? But that's how it works. Pretty cool. If your wheels have about 70% of your mass, 70% of your weight, they can actually produce as friction based off the coefficient of friction on your tires and all that sort of stuff. You can do such a simple calculation where all the masses cancel out, and whether or not your car will slip, whether or not the string will break, it's the exact same scenario. Whether or not the car will slip or whether or not the string will break comes down to nothing to do with mass in this situation of friction. They cancel out. It's really cool. I can show you a picture of it from your textbook. I think I have one here. Here you go. They talk about it in here. So Fc will equal the force of friction. If you know that that force of friction is a fraction of your weight, which it is, friction has a direct relationship with the normal force, which comes from your weight. You can tell what the velocity is, and the masses cancel out. It's entirely dependent on how sharp that corner is. That means a truck and a little Mitsubishi, what's a small Mitsubishi? Lancer. A truck and a Lancer, a little hatchback Lancer, will spin out at the same time. Except for the issue of different tires with different grips. Yeah, so snow will change this number here. It will change this coefficient of how much of our weight can actually be handled by the friction. So they talk about it here. For a wet road, the friction is closer to 50%, so this number would be 0.5. So the velocity you can handle is a bit less, depending on the radius of the curve. Isn't that kind of cool? Fun applications of physics. There you go. All right. You and I have very different views of fun. Is that what you said? Let's do some practice. You don't need to worry about that too much. I just wanted to talk about it. I think it's really interesting. Exercise. All right, let's now have a repeat of last time where I assigned your task and then I walked around 2 minutes later and a bunch of you hadn't even started. Let's go. Nicola, I wasn't kidding about moving. I know you only had a few minutes left, but you continued talking for the remainder of that period. Not next time, yeah? Am I still recording? Did it catch that noise? I can't remember if I stopped the recording. Was it recording? Yeah, absolutely. I'm going to use it.